So in thermal physics, we study the behavior of a system when the temperature of the system changes. Now, when we see a system, we're talking about something like a tank of gas or a block of iron or a bucket of water, things like that. It has a large number of microscopic particles such as molecules and atoms. Okay? Now, we start from the simplest possible way to put these molecules and atoms together. In a case of a solid, you have a strong force between adjacent molecules. And that is the force that holds the particles together. That's why it doesn't change its shape. Right? So the force is quite strong. And when you go to a liquid phase, the force is still reasonably strong to prevent the particles from flying apart, right? But it's not as strong as the case of a solid. So the molecules can slide past each other. But when you look at a gas phase, that's when the molecules are pretty far away from each other. In other words, the density is low. And because they're pretty far away from each other, these molecules do not have strong interactions among them, except for the brief moment of collisions. And if they're diluted enough, we can safely ignore the intermolecular force. So we can just think of it as a bunch of free moving particles. They don't see each other unless they happen to collide with each other. Otherwise, it's just a free bunch of particles. The fact that we can ignore the otherwise complicated intermolecular force in a dilute gas makes it the easiest system to study, relatively speaking. Okay, so as our first model of the real matter, we consider what's called an ideal gas. And the ideal gas really is the idealized situation of a very dilute gas in which the density is so low, the molecules are so far from each other that we can totally ignore the intermolecular force, except for their collisions. Okay, and we're going to examine the properties, the so-called macroscopic properties of these ideal gases. Macroscopic means something big enough for us to see, okay? Something big enough for us to macroscopic. But it turns out that we cannot quite avoid looking at the microscopic picture, because after all, as we just talked about, the reason why we study that is because we can ignore intermolecular forces. So we are actually dealing with the understanding at the molecular level. So we have to add a little bit of microscopic picture, okay? But we'll see more of that in a later chapter when we focus more on the microscopic or molecular properties of an ideal gas. For now, let's mostly focus on the macroscopic picture. And we look at quantities that are big enough for us to measure, such as the pressure, the volume, the temperature of a tank of ideal gas. Okay, so in the real world, dilute gases are very close to ideal gases. They're excellent approximations to the simple model of ideal gas. Okay, and because of the lack of intermolecular forces, the ideal gas is the simplest of all thermodynamic systems, because just put a bunch of molecules together and they don't even see each other, except for collisions. Now, let's focus on this ideal gas. What kind of law or laws do they satisfy? We're talking about laws that relate those macroscopic properties together, such as the pressure, volume, temperature, and so on. Okay, so we're talking about pressure, volume, temperature for a given amount of ideal gas. By given amount, I mean it's got a certain it's got a certain number of molecules or a certain amount of mass. Okay, so we do not change that, but we can vary pressure, vary volume, vary temperature, and how do they relate to each other? Well, it turns out historically those were studied in 3 separate laws called Boyle's law, Charles's law, and the so-called third gas law, otherwise known as Gay-Lussac's law. Each of these refer to the variation of 2 of these 3 variables. We hold one of these 3 as a constant and vary the other 2, and we obtain a very simple relationship between the other 2 variables, where the third variable is held fixed. The Boyle's law, the first one of these, considers what happens when you vary the pressure, what happens to the volume of an ideal gas when the when the pressure changes, while keeping the temperature as a constant. Okay, it turns out that when you keep the temperature as a constant, then the volume will decrease in proportion to the pressure, which means when you double the pressure, the volume shrinks to 1/2. I mean, when you add pressure, you're going to compress the gas, right? But how much does the gas shrink? Very simple. You double the pressure, you will lose half volume. And if you triple the pressure, you lose 2/3 volume and so on. That means that P is proportional to inverse of V at constant T. In other words, P times V equals a constant. Okay, that is the Boyle's law. Now, the Charles's law, in Charles's law, we hold the pressure as a constant, right? And look at what happens when the temperature changes. Look at what happens to the volume. Now, we learned that in a previous lecture that when you do that, the volume will shrink proportionally to temperature. And if you get enough data points, you will find that V is a straight line as a function of T, and you can extrapolate that straight line all the way down along to a very low temperature where the volume shrinks to 0, and that temperature, as you know, is negative 273.15 degrees Celsius. This is defined as the absolute 0 on the Kelvin scale, right? So we know that that V is proportional to T. Okay. The third gas law, otherwise known as Gay-Lussac's law, examines what happens when the volume is held at constant. So we hold it. Volume is a constant. And what happens when you increase the temperature? Well, the pressure is going to increase, right? I mean, you heat up a tank of gas, you seal it, you don't allow it to expand, so you heat it up. Obviously, common sense tells the pressure is going to rise. It in fact may even explode when the pressure is high enough to break the seal. And that means now we have P proportional to T. Okay, so all of these laws are under special circumstances. The first one, constant temperature, otherwise known as isothermal. Second one, constant pressure, otherwise known as isobaric. The third one, constant volume, otherwise known as isovolumetric. Okay, these are all special conditions. Now, have you ever wondered then, what happens if we vary all of these three together? Is there a law that unifies all of these three circumstances so that we allow each variable to change independently? Actually, I shouldn't say independent, but we allow each one of these variables to change simultaneously. And then what kind of conditions do they satisfy? Well, mathematically, it makes sense to write something like P V over T as a constant. If you look at P over T as a constant for this tank of gas, it satisfies all of these three cases, right? I mean, for example, if you hold T as a constant, then P times V is a constant. That's Boyle's law. And if you hold P as a constant, V over T becomes a constant. And that's Charles's law. And lastly, for the third gas law, you hold V as a constant and P over T becomes a constant. So clearly, this expression unifies all three of these special cases, and this is known as the ideal gas law. Okay, the ideal gas law. It's the most general version, unlike these three special cases. Now, in the ideal gas law, we have a constant here. Right? We have a constant here. What is that constant equal to? Clearly, that depends on how much gas you have, right? I mean, if I double the amount of gas for the same volume, the same temperature, I don't change the volume temperature, but I double the amount of gas inside, then clearly I'm going to double the pressure, because pressure really is because the molecules are striking the they're striking the boundary of the container, giving it a little impact. You add all the impacts up, you get the pressure. When you have double the amount of molecules doing that, you're going to get double the amount of impact. Therefore, doubling the pressure. I mean, this is a little bit microscopic, but it's easy to understand, right? So that constant should be proportional to the amount of gas you have. Does it mean the mass of the gas? The mass of the gas. Suppose I have a tank of nitrogen, 5 grams of nitrogen versus a tank of oxygen, also 5 grams. They have the same mass. Is it true that PV over T is equal to the same constant for 5 grams of oxygen and 5 grams of nitrogen? Well, believe it or not, the answer is no. What matters is not how many grams they have, but rather how many molecules they have. And oxygen molecules have different mass than nitrogen molecules, a little bit more massive. And therefore, 5 grams of oxygen actually has less number of oxygen molecules than 5 grams of nitrogen has nitrogen molecules. And as a matter of fact, if you compare these two 5 gram systems, the nitrogen having more number of molecules will actually produce a greater constant, which means, for example, if the hold V and T as both constant for both of these the same, the pressure of the nitrogen 5 gram tank will be greater than that of oxygen simply because it has more nitrogen molecules than oxygen molecules for the same mass of 5 grams. That is from experiment. So what we found was that that constant is proportional to N, the number of molecules, not the total mass of the molecules. Of course, if you hold the mass fixed, you also fix the number of molecules, but that's what's proportional to. Okay, now N is a very, very large number, right? Even for 1 gram of gas, we're talking about an astronomically large number of molecules. What if I don't want to deal with such a large number? What if I only look at the macroscopic picture, not microscopic, which means I don't deal with the actual, I don't count the number of molecules. Okay, there's a way to do that. That is, I do not count the total number of molecules directly. Rather, I divide them into a unit number of molecules called a Avogadro's number. Avogadro's number. The Avogadro's number is an extremely large number, 6.023 or 22 times 10 to the 23. It doesn't have to be molecules. Any number of particles, if they have this many, we call it an Avogadro's number. This is otherwise known as 1 mole. Okay, so the Avogadro's number is this many particles per mole. So what's a mole? A mole of any substance contains this many particles, Okay, then we call it a mole. It could be hydrogen molecules, could be electrons, could be anything, as long as you have this many. So why such a large number? Why not 1 times 10 to the 25, right? Why such a specific number, 6.023 times 10 to the 23? Well, there's a reason for that. It's a matter of convenience. Right? It's a matter of convenience. Because when you define the Avogadro's number as this much, you will find it's easy to figure out how many grams of any matter would make up 1 mole. Okay, let's see how we do that. So here again, we go a little bit into the microscopic situations, but it's not hard to understand. And as you can see, it's an extremely large number. If you want to, you don't use scientific notation, just want to actually count it in plain English, it's going to be 602 sextillion, 200 quintillions, and then quadrillions, trillions, billions, and millions. I mean, trillion usually is the largest note we use for numbers, right? Like $1 trillion, you know. But I mean, when it comes to money, this is pretty much as high as it gets. Besides that, we don't even know what it means. Okay, it's an extremely large number, but why such a number? Well, let's see here. Originally, it is defined as a number of carbon-12 atoms. Okay. Okay, it's the number of carbon-12 atoms in 12 grams. And that is, I have a type of common carbon, the most common type of carbon. It's called carbon-12. I'm going to take this many carbon-12, 1 mole, or Avogadro's number, and I count how many carbon atoms are there. It turns out it's got this many. this many. Okay, so I take, actually, I should say I take 12 grams of carbon-12 atoms. Okay, and I count just how many carbon atoms are there in 12 grams. It turns out to be Avogadro's number. So why do you take carbon-12 and count 12 grams, not 10 grams, not 1 gram? Well, here's the reason. Look at a simplified picture of a carbon-12 nucleus. The reason we call it carbon-12 is because this particular type of carbon has 12 electrons. I'm sorry, 6 electrons, okay, 6 electrons and 6 protons and 6 neutrons, okay? The electrons are negative charged, moving outside the nucleus. The nucleus is made of 12 nucleons, of which half of them, or 6, are protons, positively charged to balance the electrons. The other 6 are neutrons, they don't carry any charge. Okay, now, most of the mass is carried by the nucleus, protons and neutrons. I mean, electrons are extremely light compared with these, so we can ignore its mass. Okay, but you take a look at the nucleus, which I drew schematically here. It's got 6 protons and 6 neutrons. The mass of the protons and the mass of the neutrons are roughly equal to each other. Okay, m proton roughly equal to m neutron. And they're much, much greater than the mass of the electron. It's almost 2,000 times as the mass of the electron. Now, so think about it. Okay, you can think of roughly as 12 pieces of matter, 12 particles of almost the same mass each in each of these atoms. Okay, and I have this many such atoms. Okay, you put this many atoms together, right? Avogadro's number, and I counted 12 grams. Now, what did that tell you? It tells you to take this many carbon-12 atoms, and I do not count the entire atom. I count only one of these particles, such as 1 proton and 1 neutron, but I have this many protons and neutrons. How much do you think they would weigh? Well, I know, look, 12 of them together will produce 12 grams, right? If you have this many. If I only count one of them, that's 1/12 of the total mass. Shouldn't I get 1 gram, right? So therefore, for a proton or a neutron, they're very light, but if you take an Avogadro's number of protons and neutrons, how much do they, what's the total mass roughly? 1 gram, 1 gram. Okay, that is the reason why we choose Avogadro's number as a unit to count the number of particles. Okay, so let me write that down, extremely important. This many of protons or neutrons would have mass of 1 gram. So mass of this many protons or neutrons. All right, so 1 mole of proton roughly has a mass of 1 gram. The same can be said for 1 mole of neutrons. All right, now suppose I have 1 mole of any substance, say 1 mole of oxygen. Okay, oxygen 2, O2. Consider. So that's 1 mole. Okay, Avogadro's number is otherwise known as 1 mole. So consider 1 mole of O2. Okay, how many grams would that be? Well, for O2, look at the molecular, the atomic structure of O2. It's got each O2, the molecule has 2 oxygen atoms, and each oxygen atom has 8 protons and 8 neutrons. Okay, of course, also 8 electrons, but I ignore their mass. So we're talking about 16 protons and neutrons combined for each oxygen atom. And there are 2 oxygen atoms per molecule, so there are 32 such nucleons, protons or neutrons. And each one of these in 1 mole would weigh 1 gram, right? So we got 32 of them, 32 grams per mole. The same principle can be applied to figure out how many grams would be 1 mole of nitrogen molecules. That's N2. Okay, N instead of O has 14 protons and neutrons instead of 16. So we're looking at 28 grams per mole for N2, and so on. So look at how simple this is, right? All you have to do is count number of neutrons and protons in the entire molecule, and if you have X of them, say X equals 26, then the 1 mole of such substance would have 26 grams. It's just that simple. Okay, that is the reason why we define Avogadro's number. It's a matter of convenience. Now, given that, we can now go back here. This N can now be written as the number of moles, right, times Avogadro's number. This small n is the number of moles, okay? Big N is the total number of particles, right? So I'm going to use the Avogadro's number as a base unit for counting the number of molecules or the number of any particles, okay? And since the Avogadro's number is a constant, then I can say that this PV over T is also proportional to what? To the number of moles in that tank of gas, proportion N. Okay, so now I have finally the ideal gas law now becomes PV over T proportional to N, the number of moles for that tank of gas. But that's a constant, that's only a proportionality. It's a proportional, it's not an equal sign. You can see clearly the two sides do not have the same sign, the same unit. Okay, here is pressure times volume divided by temperature. We can manipulate the expression of the unit a little bit on the left-hand side. Pressure is force per unit area, so Newton per meter squared, that's pressure, right? Volume is meter cubed, and then we divide it by T, which is Kelvin. Okay, now the numerator is actually Newton times meter. That's the unit for work, right? Force times displacement, right? For work, and it's also unit for energy. That's joule per Kelvin. So the left-hand side has the unit of joule per Kelvin, but the right-hand side of the equation is in moles. So this is joule per Kelvin. This is in moles. Clearly, they're not the same. What's missing is a constant. Is a constant here. This constant will balance the unit and will turn this proportional sign to an equal sign. And it turns out this constant is the same for all ideal gases. That's what we call it universal gas constant. Universal gas constant. And what is that equal to? 0.0821 liter ATM over mole over Kelvin. Now, we didn't use ATM and so on, but we used the standard unit of joule. So this side is joule per Kelvin, the other side is mole. So that constant has to be joule per Kelvin per mole to balance the two sides, and that's exactly what it says here. Okay, so this is the SI standard SI unit for R, the so-called universal gas constant. You can convert that to liter, the ATM, and so on, because the pressure can be measured in ATM, right? So you can do that, whatever is more convenient for your calculation. But in the SI system, it is 8.314 joule per mole per Kelvin. This is a universal constant, just like the universal gravitational constant. Okay, it's another one of those fundamental constants of nature. And now we finally can turn this equal into an equal sign. There's when you drop in this R here. This R here. So now we have PV over T equals to NR. And this, folks, is the universal, it is the ideal gas law. Okay, the ideal gas law, otherwise known as, written as PV equals nRT. Okay, PV equals nRT. This is the ideal gas law. And you could be using that a lot. Now, there is a variation of ideal gas law. We can rewrite the right-hand side, not in terms of the number of moles, but in terms of the number of particles. And that's a small variation of that. I can write M, the number of moles, as the total number of particles divided by number of particles for each per mole, which is Na, right? Avogadro's number. So when I do that, and then I can rewrite this as PV. You have PV equals total number of particles divided by Na. Move that Na over here. Then I have T here. Now R is a constant, Na is also a constant. Therefore, R over Na is a constant. And that constant is actually very small because R, as you know, is 8 point something, right? But Na, the Avogadro's number, is 10 to the 23. And therefore, you're looking at an extremely small number. And that small number is 1.38 times 10 to the negative 23 joule per Kelvin. Okay, that constant is known as the so-called Boltzmann constant. Right here, this combination is defined as K. That's how we define it. The Boltzmann constant. And the Boltzmann constant is also a universal constant, and that appears in every equation there is about thermal physics, if you want to dig into the molecular root. Okay, look at how these molecules behave to produce the effects that we can see, such as pressure and volume and so on. You're going to see the Boltzmann constant. It's a universal constant, extremely important. And you will see the application of that in the next couple of chapters, actually next 3 chapters. Okay, so I can now rewrite the ideal gas law in 2 common forms. Okay, I'm going to, as a summary, I'm going to put both of them here. P equals nRT. Okay, this expression has no microscopic numbers, very, very large, very, very small numbers. But you can also write it down as P equals big N times K times T. Now, this time you have microscopic values such as big N, that the number of particles is a very, very large number, and K, the Boltzmann constant, extremely small number, and then multiply them together, you get a number that's not too big, not too small. Okay, so these are both valid expressions for the ideal gas law.